let's continue to look at some more examples of motional EMF. Here's our second example. I have a similar setup as the previous one, except there is no gravitational force in this consideration. This problem is one of the sample problems in the textbook as well. So I also have a U-shaped rail with a current with a resistance concentrated here, and there is this metal bar of length L that's cutting through magnetic field lines. It's just like before, but the difference is this time, first of all, there's no gravity, and secondly, I give this bar an initial cutting speed this way, okay, and I leave it alone. I don't use any force to pull it or push it. I want to know what happens to the speed as a function of time. Now, let's take a look at qualitatively how this bar should behave. If you do not have the Faraday's law at work, there's no magnetic field here, then if you do not consider friction, which we don't, then this bar is going to keep on moving forever at the same speed, right? It's never going to change. Now, in reality, what happens is that as the bar is cutting through magnetic field lines, there will be a generated induced EMF, which will then power a current, right? And that current will then pass through this bar, and this bar, with a current flowing through it, will be subject to a magnetic force under the influence of this magnetic field, and that force will influence the motion of the bar, so the bar will no longer be under zero acceleration. Its speed will change. Okay, now let's see. Does the speed increase or decrease over time? What do you think? Well, what we do in the previous problem, we look at conservation of energy, right? Look at conservation of energy here. Suppose the speed increases over time when you have a magnetic field. Then on the one hand, somebody is supplying extra kinetic energy to this guy, right? And on the other hand, a current is going to flow through it, induced current, and that current will light up a light bulb, if there's a light bulb, or generate some heat, right? Whatever happens, you're going to have an extra amount of kinetic energy in addition to extra amount of thermal energy here, even though you only have a static magnetic field that does not change over time at all. Who paid for both of these bills? It's not possible. Okay, so just like our argument before, we know the magnetic force must be a retarding force. It has to point backwards like that. There's no choice. That force will slow down the motion of the bar, so the bar is going to lose kinetic energy. But that loss of kinetic energy then turns into thermal energy that's dissipated on the bar, on the resistor. That is the only way to balance energy in this problem. So you will get a retarding magnetic force. See if it agrees with Faraday's law about the direction. Okay, let's see here. As you pull the bar this way, you're going to increase the magnetic flux inwards, right, for this area, and therefore a current will be generated, and that current will have to generate a flux outward to try to reduce the change in flux, and that must be a current flowing like that. Okay, the current must be flowing like that. So in a bar, the current flows like that, and so L cross B, L is along the direction of the current flow, B goes into paper, L cross B. Indeed, the magnetic force is like that. It opposes the motion of the bar, and that is consistent. That is consistent with conservation of energy requirement. Okay, so as a result, this bar will receive a retarding force. So V initial. V is going to start from V initial, and it's going to drop over time. Okay, does it go down uniformly? Does it go down like a straight line? If it goes down like a straight line, that means the acceleration would be uniform, which means the force will be uniform. But wait a second, the force is proportional to what? To the speed of the bar, right? Right? It's proportional to the speed of the bar, because if you increase the speed, you are increasing the rate of cutting the field lines. EMF will be greater, the current will be greater. So FB will be greater. Okay, so as the speed reduces over time, the magnetic force also diminishes over time, right? And therefore the acceleration, even though it's always a negative acceleration, it will become smaller and smaller in magnitude. Therefore the speed will reduce, but not a constant rate, but at a reduced rate. It's going to gradually decay to zero. It's going to do something like that. Okay, it's going to do something like that. And that reminds us of some sort of exponential decay, right? Like e to the negative t over tau type of thing. Okay, so that's what we suspect. Is that right? Well, let's see. To solve the equation, to solve the motion of this bar, we have to establish the equation of motion from Newton's second law. There is only one force acting on it. That is this force. Okay, so that's that force. And let's write it down. What's that force equal to? It is equal to I B L, and it's got a negative sign, right? It's got a negative sign because our positive direction is like that. And let us write down the expression for I. I is epsilon over R. Again, epsilon is the EMF in the bar. R is right here. Epsilon over R BL. And epsilon is what? Epsilon is VLB, right? V is the speed, L is the length, B is the magnetic field. So it's negative BLV over R times BL again. So just reviewing the previous problem, negative B squared L squared, B squared L squared, R times V. It's proportional to V. Okay, and that equals mass times acceleration. Okay, that equals mass times acceleration, m dv dt. See, m dv dt. And therefore, the equation of motion should be this. It should be dv dt equals to what? I'm going to move that m over negative b squared L squared over mr. That's a constant. Times v. Okay, that is the equation of motion. The equation of motion. You see, the acceleration is not a constant, depends on v. Okay, this is a typical equation which satisfies the standard exponential function, because again, you have v on one side, you have dv dt on the other side. They must match functionally, which means v and dv dt should have the same functional dependency on t. The only way to do it is to have an exponential function, so you can plug in the exponential function, or as an alternative, which we usually do not do here, is, you know, we can just move that v down and move that t over, then we can integrate. Okay, so as an alternative, why don't we do it, solve this problem this way? dv over v, I'm going to move that v here, and then that's just a constant. I can keep it anywhere I want. B squared L squared over mr, just a constant, times dt. I have moved t on one side and v on the other side. This is called separation of variables. Okay, and that allows me to integrate 0 to t. Meanwhile, v changes from v initial to the current speed v. Okay, not from 0, but from v initial. So let's finish that. That is the natural log. The left hand side is natural log of v over v initial. The right hand side is negative b squared L squared over mr times t. Okay, now solve for t. Solve for v. V equals v initial e to the negative b squared L squared over mr times t. That indeed is, as we suspected, an exponentially decaying function. Okay, so it's e to the negative alpha t. Alpha is b squared L squared over mr. That is the same alpha that we got in the previous problem. You see how these problems are connected? Okay, a large alpha means it's going to quickly stop. Okay, the bar is going to quickly stop. That means there is a very strong magnetic field. Very strong magnetic field. A very long bar. Okay, and a very small resistance called a large current. So the induced current is so great, so large, it gives you instantly a very large magnetic force stopping you. So you're going to get stopped quickly on the track. So that is our second example. Okay, and you can see for yourself. Okay, I'm not going to work out the exact equation for you anymore this time. I want to leave this exercise for you. How does energy conservation get satisfied here? And that is the loss of kinetic energy here for the bar over time. The rate is decay dt, right? That has to be compensated for by what? By the power dissipated on the resistor. In other words, the reason why there is a thermal energy release is because the bar lost kinetic energy. So can you see a conservation of energy? And how does it become consistent with the equation of motion? This is F equals ma, equation of motion. Just like the previous problem, you will see that the equation of motion, F equals ma, matches the conservation of energy. You give you the same exact result as expected. So please work on that and see if that's the case. Okay. Now, our next example of motional EMF. The difference this time is that I'm using a bar to cut through magnetic field lines in such a way that different segments of the bar has different linear speed. In particular, I have a rotating bar with one end fixed, and the entire bar will rotate about this end with an angular speed omega, okay, in a plane that is perpendicular to the B field. The B field gets points into the paper, as always. And there is a length L. As a result of cutting, there will be an EMF at the two ends of the metal bar. There will be a potential difference, okay? And I want to know what is that potential difference equal to, and which side has higher potential, which side has the lower potential. So basically, by forcing this bar to turn in the magnetic field, you have turned this bar temporarily into a battery, into an EMF. I want to know which side is positive, which side is negative, and what is the potential difference. Okay. And we're going to do this problem with two methods. Okay. Method number one is from the concept of motional EMF. You know, after all, the reason why there is a EMF generated is because this bar is cutting through magnetic field lines, right? Now, the complication here is that different segments are cutting through field lines with different speeds. So what I need to do is I need to isolate a little segment out, and let's see this particular segment moving with its own speed, v, okay, which varies from place to place. How does it contribute to the EMF? All right, this little segment whose length, I'm going to call this the R direction. Okay, I'm going to call this the R direction. This is O. This little segment is between R and R plus dr. So it's only got a length dr. So as it cuts through the field lines, what kind of EMF will be generated across its two ends between here and there? What is d epsilon? That's what I want to know. What is d epsilon equal to? Well, remember the formula BLV. L is the length of the bar cutting. Here the bar only has a length dr. Okay, so it's instead of BLV, it will be B times dr times V, right? So it's B times dr times V. V is the speed of that particular segment, which is what? I'm going to write down V first, but I know it is just omega times R, right? R is the radius between here and there. That is d epsilon. It's the potential difference between this point and that point. Okay, now, every one of these segments will generate its own d epsilon, and the total potential difference between this point and that point will be what? Will be the sum of all these d epsilons. Okay? So therefore, epsilon, the potential difference between the EMF generated between the two ends, would be the sum or an integral over d epsilon, and that will be equal to what? B and omega, these are constants. We're taking them out, or dr. Right? 0 to what? To the length L. The integral is very simple, 1/2 L squared. That gives you 1/2 B omega L squared. Alright? That is from the concept motional EMF. Every one of these segments of the bar is cutting through the magnetic field lines with its own speed. We find d epsilon from each segment, and then we integrate to add all the d epsilons up. Now, interestingly enough, this final expression can be rewritten in the following sense. You know, if you cut this field lines uniformly, at the same exact speed for every segment, the answer would be BLV, right? BLV, right? But in our case, different segments are cutting with different speeds. So I'm going to have to use some sort of average speed. Make sense? Okay? And what kind of average speed should it be? Well, here the speed varies linearly, okay, from 0 to maximum value at that end. For any linear function, what do you think the average value is? Well, the average value is the value at the middle, right? For any linear function. You cannot say that for this arbitrary function. For a linear function, that is definitely true. So in this case, it's this speed plus that speed divided by 2. Alright? B, L, and then this speed, which is 0, plus that speed, which is what? Omega times L, right? And you divide it by 2. You see, that is 1/2 B L squared times omega. See, that's the same. Okay? So really, The reason why we got that answer is because I have to use some sort of average cutting speed over the entire bar, and since the speed changes linearly, I only use the speed in the middle, okay, as the average speed. So there we go. That is our first method, using the idea of motional EMF. Now I wish to solve this problem from a different perspective. Okay, the algebra is about the same, but the idea is slightly different. This time we're going to revert to the original Faraday's law of induction. In the original law, all I care is d phi b dt. I don't really care whether it's due to the motion of the border, like in this case, or is it because B changes itself, whatever. So, if you want to apply the original Faraday's law, you don't think of cutting the B field lines. Rather, what you think of is, imagine there is a certain region or certain area in space. I'm going to find the magnetic flux through that space and see how that space changes, how that flux changes over that space. This bar here does not in itself complete an entire space. I need to therefore imagine some more segments to complete a whole area, okay, or a whole space. So what I'm going to do is this. I'm going to assume there's a fan-shaped area like this. Why do I choose a fan-shaped area? Because obviously, you know, this is, if you choose a fan-shaped area, then as this tip moves, it's easy to calculate how the area grows. Okay, if you use a complicated area border, then what's the point of doing that? Alright, now suppose initially the bar is here, and gradually it made its way over there. And this angle, therefore, I can write as what? Omega times t, right? Omega times t. Now, this area is made of two imaginary border lines and one actual bar. It doesn't matter whether it's imaginary or real, but what's important is that this bar is the only part of the area that actually moves, that actually shifts. So I don't have to consider here and there. They do not contribute to the EMF. This bar does, because it rotates. Okay, what I need to do is find the flux, the magnetic flux going through this area. Okay, and then I'm going to see how it changes. What is the rate of change of that flux over that area? That should be epsilon, right? So that was, over there was method 1, and over here I find method 2. Phi b, first of all, phi b, what is that equal to? You know, over that fan-shaped area, the magnetic flux, the magnetic field is uniform, so it's just A times B. The area of the fan times B, that's it. B doesn't change, but A does. Okay, so what is A? A is what? For a fan-shaped area, if the angle here is theta, and length here is r, do you remember what the area is equal to? Well, the area is 1/2 arc length times radius. Okay, arc length theta times r, and the radius is just r, so it's 1/2 r squared times theta. R here is L, from here to there is L. Theta is omega t, right? So you see, the area changes. It's proportional to t. It grows as time increases. Makes sense. Times b, okay, the magnetic field. Now, what is d phi b dt? What is that equal to? That equals to 1/2 L omega b. In fact, right? So it's just d dt. Let me copy that. 1/2 L squared omega b, and then times t, and all these constants taken out, you just get 1/2. Or you can write it as b omega L squared, same thing. That, in fact, is the magnitude of epsilon, right? The magnitude of epsilon. You know, here I also calculate the magnitude of epsilon. I didn't write down this negative sign because that negative sign only tells the direction of epsilon. So I'm just comparing the two magnitudes. You see, you get exactly the same result. Okay, but once again, conceptually they're a little bit different. Okay, they're a little bit different. With the first method, I focus my attention on the motion of the bar, cutting field lines, therefore causing EMF. In the second method, I imagine there is a virtual area which grows over time because this side of the area increases.